And seeing as we have our first speaker here, Joe, I think we might start.
Okay, I'm going to see if I...
So I might just do a quick intro first, Joe, if that's okay.
Oh, okay, absolutely.
Sure. So big welcome to everyone who's joining. I just wanted to let you know that we will have 4 speakers here today, and we will have a short break in between them just so you can go and grab another cup of coffee or tea if you need to. So welcome to those of you who are joining from all sorts of various places around Australia and even the world in Joe's case. For those who don't know me, my name's Chloe Thompson and I'm the Executive Officer of the Victorian Strawberry Growers Association. This webinar about robotic opportunities and possibilities in the berry industry has come about thanks to some funding from AgriFutures Australia. So the VSGA applied for this funding and we were awarded it to run several workshops for strawberry growers and berry growers. So yeah, it's really exciting that thanks to Zoom and perhaps thanks to COVID, we're able to invite a huge range of participants from around the country rather than just having a face-to-face workshop. So a particularly warm welcome to the VSGA grower members and associate members who are joining us today. And I think the only other thing that I need to let you know about is asking questions. So after each speaker, we will have a question time, around 5 to 10 minutes, just depending on how long the speaker goes for. If you would like to ask a question, you should see a chat box or the chat function somewhere on your Zoom screen. If you just push chat and then you can type in your question, that's the easiest way to do it. If you would like to use your voice to actually physically ask a question, then you can push the raise hand function, which looks like a little palm on your Zoom screen. And if there's time, then I will turn on your microphone so you can talk and ask a question that way. So I think without further ado, I will jump over to the first speaker, which is Joe Mcgee. Now, Joe actually is from Harvest Crew Robotics, and he is currently in Miami in the US. Is that correct, Joe?
Slightly north, Tampa, about
Tampa, there we go, it's close. But so anyway, it's nearly midnight where you are, so that's why we've got you up first, so you don't fall asleep.
Right.
So, Joe, I might ask you to share your screen so that everyone can see your presentation.
Okay, can you guys see this?
I can see it perfectly, that's perfect.
So I've got hi guys, my name's Joe Mcgee. I'm obviously not from the US, but from Scotland and been around the world. I ventured onto my first strawberry field about 2.5 years ago. I came out of retirement to help these guys with this company. So I'm going to go through about a dozen slides of where we are in the development of the product. And then I have about a 3-minute video that I will show you that will kind of finish up the presentation, and I'll do some Q&A. So I was initially on the board of the company. I came off the board to be the executive chairman, and I've been the CEO for about the last 2 years. I have a PhD in mechanical engineer, thermodynamics and fluid mechanics, and I have my MBA, and I worked for probably a $26 billion company doing product development for many years. So this is our product in the field in Florida. This is on a 700-acre farm. And I will go through some quick slides. So the CREW stands for Computerized Robotic Optimized Obtainer, which is a mouthful, which has been abbreviated to CREW. We believe this is the first fully automated strawberry harvester, so that the machine will actually identify the strawberries, determine if they're ripe, create a targeting solution, pick the strawberry, transfer it, sanitize it, optically inspect it for issues, and then pack the machine and put it into a cold chain, all on the upper deck of that machine. A couple of things about the history of the company. The company was formed by a gentleman called Gary Wishnowski and Bob Pritzer. Gary runs about a $350–400 million strawberry operation on the West Coast in California and on the East Coast in Florida. We have 70% of the strawberry industry in the US is actually on our cap table, so they have actually funded us. Our development has been done with a lot of collaboration with the growers, very specifically about what they want. They do not want a harvesting aid, but they want a complete human replacement. Our development has been on the various growers' operations, and we are actually financed a great deal by Farm Credit in the US, which is a co-op designed to create self-sustainable food production for the US population. What we're going after, and I've chatted with some of the people in Australia, and I think your problems are maybe not exactly the same as ours and the US, but we've got out of the market, which we think is about 22.5 billion, about 4 billion is in the US, and of that 4 billion, about 40% of that revenue is actually spent on labor costs. I'm not sure if that's familiar or not. The workforce here is now predominantly migrant labor that is brought in from Mexico under a thing called an H2A program, and COVID obviously had its impact. And we have minimum labor salaries being enacted, particularly in California a couple of years ago, and now in Florida. So we're expecting that labor cost, which is about 1.3 billion for that 4 billion market, to go to about 1.9 billion over the next 3 or 4 years. The labor issues here result in about 25% of the fields actually going unpicked, which is lost revenue. Let me think. So what we intend to do is we don't intend to sell or lease the machines. We will actually operate the machines. The machine is completely autonomous. There is nobody on it. And just like flying a drone, we control those harvesters from a central NOC, and we will give them a work program. We will map out a field, and then we will stay in the fields in Florida for 3 or 4 months. Then we migrate the machines to California, where they pick for about 8 months. The US market is 85% in California and about 15% in Florida. The system has got about 12 modular items on it, and that's because it's designed not just to do strawberries, but can actually do a range of other products or produce and fruit. I'll probably not jump into how the machine works because I have a video at the end that will show you, and then in the Q&A we might get into some of those questions. Again, as it says, the chassis holds about 16 robots underneath it. The field layout is very important to us. When we look at the pitch between the furrows, that's an important thing, and we do have variation in the US, so we are looking at those guys to either optimally design the field around us, or we have to change the machine. I think once we prove the machine works, our customers who are on the cap table have told us they will reconfigure the fields. The robot is hot swappable. It just plugs in, takes about a minute, and we can then switch that out. Let me just go through. So kind of hit on this quickly, but the way the harvester works, it will go down the field, it aggregates the leaves, it then spins around, it sees what strawberries are ripe. It can predict the ripeness of the strawberry about 2 weeks out. It will then create a targeting solution, pick that strawberry. It will then transfer the strawberry into a solution which is proprietary, and it does E. coli, Listeria, and Salmonella. It basically removes that. We don't touch the strawberry with a human hand, so we don't have any Hep A or rotavirus or COVID-19. We also have the ability in the solution to hydrocool the strawberries. So in Florida, the temperature here, probably 95, 100. We can cool it down to about 55 to 60 degrees in about a minute and a half. We then can actually weigh, or we then optically inspect the strawberry, and you'll see that in the video. So when we pick the strawberry, we only see the top half. So we have to inspect the bottom half to make sure it's okay. Then we weigh the strawberries and we determine a predetermined weight, and then we load them into the clamshell. We vibrate them, we then dry them, and then we keep them in the cool box, and then they're transferred to the cooling shed for distribution. We are looking at harvesting as a service. As I said earlier on, we will operate the equipment, we will do the maintenance, both field, depot maintenance, logistics. And again, I apologise for not knowing necessarily the Australian food safety systems. Here we have to comply with 4 food safety protocols. There's one for the pickers, there's one for a harvester, there's one for the cool pack room, and there's another one for the processing house because we use a fluid. And we are effectively going in, and we've offered a solution that's paid per flat. So we just actually replace what humans do. On the sustainability side, big issue right now, we've had third parties independently look at our carbon emissions, so it's substantially below that of human harvesters. We are looking at fairly significant yield enhancement and waste reduction. On the, in the US, the strawberries are graded by the manual pickers, which we've identified there's a very significant variation. We can put those strawberries that are manually picked through our inspection system, and it will reject 25 to 35% down to a USDA grade 1 standard. The initial results with that grading, with the pathogen reduction, we're seeing a shelf life extension of about 6 days on that, which is significant when you go talk to the retail environment. There's a lot of data we gather because we go over the plants every 3 days. We have the images. I won't go into it, but we can see pathogens on a plant. And with the machine learning, we can identify what those pathogens are and give you the GPS location in a field of where the issue is. We can also, on the data, we can tell you the yield per plant, per acre, per varietal, and we can actually track that as it relates to weather and how that corresponds to it. We can look at that and correlate it to the soil information, basically the sprays and the nitrogen and the nutrients that apply to the field. We can correlate that to a yield. So we do a season. We did this season in Florida. We finished this in May of this year. We got to about 85% of human performance with the harvester, and we actually commercially picked, sorted, and fresh packed the strawberries and invoiced and paid for them. So that was a big element for this year. We have all the grading results, and we've been able to take a USDA grade 1 and divide that into 6 standards, each one being acceptable to the retail store. And with that brings the possibility of differential in pricing. And again, I mentioned the shelf life. I think we will start our first commercial trials where we'll go out and just run the harvester for commercial trials, and that will be this October. We will punch the field, and then we will go pick that field in December through May. So that was really, really quick. That was about 10 minutes. So I'm actually going to do this. And hopefully I have the correct bandwidth to do this.
At Harvest Crew, we're at the forefront of automated agricultural harvesting services, and we have set our initial target on the $24 billion global strawberry market. We have created a modular robotic vehicle that automates the harvesting, grading, and packing of strawberries. Each harvester has 16 independently working robots outfitted with our vision system and vision AI. Our harvesting services are the only option available to growers to provide a complete manual labor replacement. With our vision system, we gather 360-degree images of each plant. As each berry is scanned, we're able to determine if it is ripe, healthy, and ready to be picked. This information can then be used by growers to assess plant health, detect disease, and project yields. Through the eyes of our vision system's dual cameras, and played back at half speed, this video helps illustrate the immense amount of information that is being processed in real time. Here, the targeting system identifies ripe berries and their coordinates to ensure the exact placing of the picking claw. Played back in real time, the plant is scanned, then the berries are targeted and picked within seconds. Our secondary inspection system received a grant from the National Science Foundation as part of their Innovation Research Program. This system produces a 360-degree view of each berry, which allows our neural network to analyze the images and grade the berries for fresh pack or process within 15 milliseconds. With our harvester-mounted LiDAR system, we now have 360-degree, three-dimensional data of the fields, plants, and all objects below and surrounding the harvester. This allows for more precise navigation down rows of strawberries and provides 3D view to the harvester, so it does not collide with growing rows, people, and other obstructions that are in the harvester's path. Our software system provides actionable data for growers with information on entire fields and with detail down to an individual plant. With real-time reporting and forecast projections on berry yields, growers can make better informed harvesting decisions. We are devoted to developing environmentally friendly and truly sustainable harvesting practices. Our harvester will significantly reduce CO2 emissions, reduce pathogens, and minimize the number of strawberries typically discarded in the field. We meet and exceed food safety requirements by providing a clean, safe, and consistent harvesting method for growers. As dusk arrives, our harvester continues to pick day and night. For our growers, that means the opportunity to optimize their schedules, improve yields, and increase profit margins. While the harvester is impressive in itself, once you get under the hood and witness the flurry of robotic activity, you begin to see the huge impact automation will have on the agriculture market. Through our initial focus on harvesting strawberries, one of the most challenging fruits to pick, we have created a technology that can be adapted to a range of other fruits and vegetables. Harvest Crew is on track to scale our fleet and to fulfill the needs of growers with our innovative set of technologies. To learn more about Harvest Crew and discover how we're about to revolutionize the agricultural industry with our automated harvesting services, please visit harvestcrew.com. Thank you.
Okay, so that was my 20 minutes. So you now have your 10 minutes of questions. I rushed through that. I apologize.
No, Joe, thank you so much. That was extremely fascinating. Joe, I'd love to thank you very much on behalf of everyone for your incredible presentation. I'm blown away, and given by the number of questions, I think a lot of other people are as well. You're getting a few thank yous in the chat box, which is incredible as well. For those of you who joined late, Joe is joining us from over in America. So he's off to bed now. So again, Joe, thank you for your time. And if you want to stick around, then please do. I just ask you if you put yourself on mute if you wanted to stick around. Otherwise, we will forgive you if you want to go to bed.
Okay, well, I'll finish my glass of wine. I'm actually drinking a Molly Duke or 2 left feet, believe it or not.
Oh, there you go. All right, Joe. Well, our next speaker up is Professor Salah Sukarin. If I'm saying that correctly, Salah.
That's good.
Close enough. So Salah, if you would like to share your screen and begin your presentation, that would be fabulous. Sala is joining us from the Australian Centre for Field Robotics based in Sydney in New South Wales. So thank you, Sala.
Thank you, Chloe. And can you see the slide?
I can see the slide, yes.
Great. Okay, excellent. Thank you. Thank you, everyone, and it's great to have this opportunity to present. Chloe asked me whether I could just give a talk around some of the robotics work that we have done, which is not in berries, but then also to add some elements about what I have understood about automation and robotics in the berry industry. So this presentation is broken up into two bits. One is what my background is in the robotics area, predominantly in horticulture, and that was work that I did at the University of Sydney. And then about 2 years ago, we spun out some of that technology into a company called Agris, and that's local in Australia. And we have robots now in Victoria and in Queensland, again, mainly in the horticulture industry. So that's the first part. And then that will also give a bit of background as to why we've been doing robotics. How that may help us understand some of the aspects that are happening within robotics in the berry industry. So this is just some of the funding that we've received from various groups around the country, and we've built robots and real-time AI systems, so artificial intelligence that sit on the robot that do work on the ground on the farm. Just a snapshot of the different robots that have been built, predominantly in the hort industry, as I mentioned before, but we have dabbled in grains and also in the cattle industry. A lot of our focus has been on smaller robots, solar electric robots that can operate for long periods of time. So on batteries alone, they operate about 10 hours. And with the solar panels, we've had endurance trials up to 24 hours running on farm. But then the big question is, what do those robots do? So this is just a video of a robot going along a farm, a lettuce farm in Victoria. I'll stop it every now and then just to kind of talk through some of the things. Here it's doing real-time lettuce detection and also crop size estimation for the lettuce. So it's giving some indication of yield estimate as we move along through the week. So every week the robot will go out at least once. We can, from that information there, we can do some estimation of yield size. So you'll see some blue circles popping up on the lettuce here, which is giving some estimate of yield. Because you can detect the plant, you can also detect other things such as weeds. And this is one of our first attempts at non-chemical weeding. So using a little mechanical device that can actually scratch out the weed and avoid the crop. And so that's just doing real-time weed detection and weed removal. But also you can target individual plants and spray individual plants. So here it's doing precision spraying on each individual plant. And it determines the right location, but also how much to dose that individual plant. In this case, it's corn. So it's just showing you real-time ability to be able to do that. And here we have a water conductivity sensor. So it's measuring water, potential water conductivity at any location you want along the farm. So you can then build up a map of what the water looks like under the soil there. So in essence, what's being built is a 24/7 digital agronomist that has the ability to be able to do things such as remove weeds or spray individual plants. And that's really what the function of the R&D was all about. Same thing applied to the tree crop industry. In this case here, we're looking at apples. And what you'll see here is this the bot going up and down the rows, detecting apples in real time and looking at apple density. And then it has a targeted gun that you'll see there, and it's just spraying each individual apple as it's going through. Again, looking at it from the engineering perspective, what we're trying to solve is, can a robot in real time detect individual apples and spray individual apples? Now, whether you're spraying apples or spraying flowers or spraying the foliage around the apples doesn't really matter. It's just showing all the engineering solutions coming through together in that solution. To kind of get closer to the harvesting point, this is some indoor activity where we looked at what it would mean to kind of look at harvesting citrus. Relatively easy because as a robot, you're looking for orange objects in a green environment. And so that becomes relatively easy, just like what you saw before. Being able to detect red fruit amongst green is a relatively easy task. Picking the red fruit obviously is a much harder process, but I'm sure Joe would also attest to being able to detect a strawberry amongst the strawberry, or an orange behind an orange, or a part of an orange behind leaves is quite a difficult task. And I'll explore a little bit of that when we talk about the berry solutions. This is one of our first attempts at doing it outdoors, but what I want to touch on here was taking the same robotic arm and applying that into the context here as summer fruit. So it's a much more, a difficult fruit to grab because you don't want to damage the fruit. And so one of the things that I wanted to talk about here a little bit, because that will help us understand a little bit about the berry harvesters, is soft grippers and what we call ion arm robotic technology. So it's a robotic arm. It has sensors on the robotic arm to detect how to pin down on the individual fruit, almost like you would see in terms of satellite docking stations. So nothing's absolute. It's not using GPS or anything. It's got to come relative to the location of where the fruit is. But then looking at soft grippers, which in this case here is meant to mimic something like the human hand and not damage the fruit or anything like that. So it has little pneumatics, and in those pneumatics you can compress the fingers, and the fingers will then come along and grasp the fruit. And we've had, this was our first attempt, so there's many failed attempts and working attempts, and trying to understand what the differences are between how that might work. So this is the sensor on the end of the robotic arm, and then being able to explore what it would look like for applying these soft grippers in there. So a lot of that technology I mentioned was in the R&D lab, and in 2019 that was spun into a company called Agris, and Agris now rolls these solar electric robots out across Victoria and Queensland, looking predominantly in the horticulture industry, but it's a very modular robot, so allows us to kind of explore different crops as well. And we have tried this spot out in tunnels in berries as well, so it works quite well under canopy amongst the in our case we tried it in blackberries, and also sorry, not strawberries, blackberries and blueberries. So with that as a background, I just that was really trying to give you a flavour for the fact that a lot of the technology is available in Australia. It hasn't been applied to the berries, and obviously not at the level of expertise or experience that Joe just showed with Crow Robotics. So the rest of this presentation, what Chloe asked me to look at was to kind of explore some of the drivers that are happening with robotics in the berry industry and how that may just kind of give us a bit more information, insight. There's a publication just recently that's saying that, where have we been when it comes to fruit picking robots? It's been around in the universities and in R&D labs for a long time now, so just over 20 years. People have been looking at what does it mean to robotically pick fruit, and in particular soft fruit. It's only recent that we've seen a lot of that traction, and probably two critical factors: the market driver, which in this particular case has been labour cost. That's really kind of driven the interest, and the other one is what are the enabling technologies. And I'm gonna touch a little bit on the labour cost element, because it's an important insight that we need to keep in mind when we look at robotics for harvesting, and also touch a little bit on the key enabling technologies. So one of the first ones is around crop artificial intelligence and its application to machine intelligence. So being able to look at how computer systems and linked to computer vision techniques, and whether it's just computer vision, you could also use infrared techniques. You'll see that there are different ways of being able to do it. But what you're seeing here is the ability to be able to, what we call segmenting out the object. So the different colors there is the computer system being able to identify different fruit. And that's important because you want to be able to identify in different fruits so you can actually localize where that fruit is, and being able to kind of go through the different stage growth of the fruits to say what fruit is ripe and what fruit is not ripe. But also more importantly, as you'll see in some of these images where you can see the different fruit, is fruit being occluded. So other fruits sitting in front of other fruits. So can you identify fruit that's sitting behind other fruit, or can you identify fruit that's behind a leaf? And use that as a mechanism to try and understand whether you should be harvesting that fruit or not, because you want to minimize how many passes you go over. We're seeing a lot of technologies now where the robot can identify the fruit, but if part of the fruit is being included by a leaf, a human can actually kind of do some self-induction and determine, yes, that fruit that's hidden behind, half that fruit that's hidden behind a leaf is still a fruit to pick. And we're still not quite there yet with the robotics, or we are starting to see some solutions, but not quite there yet with the robotics. This is just another paper that's talking about different algorithms and the application of those algorithms. So on the far left is the ability, is a certain type of algorithm which is just using standard computer vision techniques, which isn't able to segment individual fruit. So it kind of lumps all the fruit together. While on the far right, some of the algorithms that you see here now is Yolo. So if you have kids, Yolo stands for you only live once, but in computer vision techniques, it's you only look once. And so it's an algorithm that allows you, just as the first image that comes out from the computer, can it identify individual fruit and can it classify the ripeness of the fruit, whether something's ripe or not ripe. So that's on the left, and on the right is using the algorithms to determine a picking angle. So if you can identify fruit, which is great. So in this first image up the top here, you can identify the fruit, but it puts a bounding, what we call a bounding box around the fruit, and it kind of gives a central axis to where the fruit is. But in the bottom, there's a newer algorithm, again, looking at rotational angles. So being able to not only detect the bounding box around the fruit, but the angle of that fruit. And that helps the robotic arm to come along and determine which is the right angle to come in at and pick that fruit. And that's an important, something that we as humans would do all the time. But as a robot, being able to identify the angle of that fruit is important so that you can identify where to come in, at what location to come in at. So that's the first part of the technology that's really kicked in over the last few years, which is machine learning and machine intelligence and using that for computer vision. And the other one is around the soft robotics. So harvesting citrus or harvesting apples harvesting avocados is okay because they're hard fruit. You can come along with a different kind of gripper and you can grab it. But when it comes to berries, you want to be able to use some soft technology. And that's really kicked off over the last maybe 3 to 4 years, where we start to look at soft grippers. So looking at pneumatics, looking at material now that can actually mimic what the human fingers would be able to do, or the human hand would be able to do, is quite a novel piece of technology that's really kicked in over the last few years. So this is some work that was done recently where they actually took, so if you look at this bottom picture over here, little finger sensor, a little sensor at the top, and they built little gloves where they put that sensor on the gloves, and they had human pickers go out there and pick the fruit, and from that measure the forces that were being applied by the human pickers, so that they could then mimic what they needed to do on the end of a human picker, so on the end of a robotic picker. So measuring those forces by a human picker, building a device which is using silicon fingers here and pneumatic, and being able to use a stepper motor, and then they could come along and use those pneumatic fingers, the silicon fingers with the same force sensor to pick blackberries, as an example. So that was kind of using humans to measure forces, then apply it into a robotic arm, and then tell the robotic arm and the robotic gripper not to pick any harder than this force. And so the two areas, so machine vision and artificial intelligence coupled with pneumatic devices, are coming together now, and they're being applied onto robotic arms in that context. The next thing I wanted to talk about before I show you some examples is about the system as a whole, and the system can get quite complex. So this is some work that was done out of Denmark, I believe, using a different type of gripper, and I'll explain a bit later about that. But I'm not going to go through this. I just wanted to show you the complexity of the process that happens inside a robotic system, where you're trying to mimic what a human does. So, acquiring data, processing that data, moving a robotic arm, coming in at the right angle, reaching out for it, touching it softly, not damaging the fruit. What is the best way of grabbing that fruit? Do you pluck it? Do you pull it? Do you twist it? And all those things come into that state machine. And all of it has to come in a very probabilistic manner. So as humans, you're kind of assessing the situation in real time as you're going through to pick up a strawberry or blackberry or blueberry or whatever it might be. You're feeling, you're touching, you're kind of grasping, and you have to try and codify all of that. And when you codify all that, it's all uncertain. So it's great to see something like what we just saw with the Crew Robotics, because it's showing you that the capability is all there to kind of reach in and do that. And if you can do that properly, then you can start to achieve some real-time harvesting results. In this particular case, where they're looking at strawberries, if I show you the top right picture first, what it's done is if you remember what I mentioned before about occlusion, it's trying to detect strawberries that are probably occluded behind other strawberries. So what is the right angle of approach to come into to harvest those strawberries? In this particular case, it's a little canister device that opens up and reaches into the strawberry and cuts the stem. And so this is looking at the canister device inside So you can see the little cutter there. So this, looking at it from the inside, they open up, it comes across the fruit, it closes, the snipper comes along, kicks on the stem, and the fruit drops down to the bottom, and then the robot will go and drop it off at another location. So I'm just going to show you some examples, knowing that the Crew Robotics guys were going to be on. I tried to find other examples just to give you context, but it's not to show where something is relative to something else. I really just want to talk about the technology, because that's what I was asked to do, just kind of talk about the technology a little bit and see what's going on there. So in this particular case, you'll see what's going on is a little robotic harvester, and I'll just slow down a little bit as they're going through. I'll stop it at one point just so that you can see the different bits and pieces coming together. And probably around here. Whoops, that wasn't meant to happen. Sorry, is that going to work? I think I'm clicking on the wrong bit. Okay, so what you've got here is you've got the soft grippers, which I mentioned before. Okay, so it's again and punched by some pneumatics. So you can see the little pneumatic valves that are there, and they cause the soft grippers to just close and open as you're going through. But you've also got a little vacuum system here. So the vacuum system, so you've got the vision system, which is detecting where the fruit is, positioning the robotic arm onto the fruit, and then this thing here will suck up the strawberry, so it takes it off the ground, and then the grippers will come through and then collapse on the strawberry and pick the strawberry. So I'll just play that so you can see that in operation. So you just see how it's just sucking it up, gripping, and then moving the fruit across, and it's trying to pick the red ones, obviously, as it's going through and picking out the fruit and detecting the fruit. So just a different approach, and it's then pushing it onto the punnet there, and then moving the punnet across as it's going through. It doesn't have the rest of the steps that Joe was mentioning before. Okay, so that's just showing you again one example of that. This is AgriRobot, which is in Spain. A slightly different concept. It'd be again some robotic arms coming through, moving along an XY axis as it's going through, and just cutting off the stem. So it's just now picking out the stem, but it's also a modular one that uses in greenhouses as well as in outside in the field. But it's detecting where the strawberry is and just cutting off the stem and pulling off the stem from there. Okay, so it's a slightly different application, and I don't believe they were checking ripeness. It's just looking for like a full red color compared to the other colors that you might find within the harvest plot. Another example, in this particular case, it's snapping the stem. So it's the soft gripper detecting where the fruit is and then kind of snapping it off at the end. Okay, and these guys, I believe, were, and I'm not going to guess what country they're from, but they've just come out over the last 2 years. But you're just seeing the different sensors here coming through, again, detecting, positioning where the robotic arm should be, grabbing it, and then trying to grab it at a certain force without putting too much force on it. Again, learning what that force is, and then having that snapping effect that you would that for them is sufficient. And the last one is Traptic that I want to show. This was a video that showed the history of the arm as they were being developed, and just showing you the last solution in this particular case. So this was one of the first robotic arms, and then the second one in 2017, twisting motion. And this is the one that they kind of stuck with, which was what we call a Stewart platform, but it's inverted Stewart platform. So if they'll just go through some of the engineering here. But this is the part where they've got an inverted Stewart platform so it's one robotic arm moving around and picking at the fruit as it's going through. So I'll show you a video later of it out in the field, towed by a tractor. So it's not itself is the robotic arm is what's autonomous, being towed by a tractor, as opposed to the platform in its entirety being an autonomous part. But again, you can see the soft gripper. So if I just jump back a bit, you can see the soft gripper, which is again some of the pneumatics. So just see it in here, right? Just picking out and kind of molding itself around the fruit before being picked. So the final one that I want to show is on raspberries. Again, just being able to how do you come in to pick, and the movement of the arm. Now again, a soft gripper, moving the arm so that you can pull it in a downward fashion, checking for any obstacles along the way so that you can grab it, pick it downward fashion, and then pull it and pull the fruit off. Okay, in that scenario. And those were the guys at Plymouth. So I just wanted to kind of just be able to kind of talk through that process and just show what that was. But I think the other thing that I think is really important is being able to look at what the scenario is when it comes to harvesting cost and harvesting capability. So this is a table showing some work that was recently done around looking at around the economic viability of harvesting. And it's important that we look at this concept. This was a study that was done in California when they were looking at labor costs around that process, and really being able to understand what the solution looks like. And in this particular case, they were looking at, so if you look at the bottom, sorry, the top right, the top left, sorry, the piece rate, cost of production, and what the net income per acre was in that scenario there. In table 2, they looked at the robotic harvesting against efficiency, so 40% efficiency, 50 all the way up to 90% efficiency. And obviously for the piece rate elements, what becomes, you know, when the costs are increasing and the efficiency is up high, then that's where the benefit's going to come into. And in the top right-hand corner, it's showing you what the piece rate would look like according to different harvesting speeds. So how many seconds it takes to pull a berry per arm, so depending on how many arms you would have, and Joe mentioned this before about having multiple arms with multiple rotating end effectors on it compared to having one robotic arm. But then there's a speed function, so you know whether you can move that robotic arm around quickly enough. So this is the harvesting speed in seconds across piece rate, and again looking at it from that context. And then what happens, so this is just using one robotic arm and no people coming in afterwards to harvest what was left over. While this one here is looking at harvesting efficiency, again with piece rates, but looking at the harvesting cost. And the benefit only happens again when you start to have increasing cost in the piece rate and obviously at high efficiencies. And in this particular case, the robot does most of the work, but the humans come in afterwards and then pick out what's remaining. And maybe the robotic system is also detecting what fruit was left over. So you're making it easier for the humans to kind of, the labor to come in afterwards and pick it. So I'm saying humans because the last 30 years I've been thinking as a roboticist. So I keep thinking of the difference between robotics and humans, right? So that's on that case there. So that's just one thing to think about, which is that efficiency is important, speed of activity is important, but then in some cases they're harvesting as an aid tool as opposed to full harvesting may be something that would be just as important for the growers. That is, harvest most of the crop or some of the crop and then indicate where the rest of the crop needs to be for the rest of the harvesting. And the last slide I just wanted to point out, and I think it was touched on in one of the questions, is the need to understand how robotics would fit within the context of the operation, because in many cases you need to, and even in the vegetable industry that we found, even with our commercial offerings for the vegetable industry, is if you'll have to change some of your operations, and that whether that's the terrain structure or whether that's access to the field or whatever, some of that changes because otherwise you're putting all the work and all the effort onto the robotic solution, which just increases the cost of the robotic solution. If you can work on changing the operations of the farm, you can actually reduce the cost of the operations of the robot coming in, and that also opens up an opportunity. So that's the end of the presentation. I'm hoping what I've shown is the technologies there. In Australia, it's working outside of the berry industry. So we've done a lot of work in the horticulture industry, but we've just started into the berry industries for small robotic configurations. The two main pieces of technologies that are really advancing at the moment now, allowing this to happen, is the robotic grippers. So being able to build soft grippers that work well, as well as the computer vision techniques, and the two things coming together to allow speed and efficacy really coming through on the robotic system. But then from a grower's perspective, looking at it in the total return cost, looking at both labor and also the operational changes that need to happen on farm to introduce robotic solutions in. Thank you. Thank you
so much, Sala. That was really interesting. I think we've got a couple of questions that have appeared in the chat box. Sam asks, from your experiences, do you think that the way that we are farming will have to change to accommodate the robotics, or can the robots adapt? You kind of covered that in your last slide, but you're suggesting it does need to change a little to accommodate the robots.
Yeah, one of the first projects that we got when I was at the university was for tree crop applications, and the big thing they were interested in was harvesting. And straight away, this was 10 years ago, straight away we could say that you could spend the next 10, 15 years trying to build harvesting tools, for different types of tree crop configurations, or you could come along and trellis all your trees, and that would just make life so much easier. And that's what we're finding now. So for those farmers that have come along and done trellis configurations for their tree crops, automation has come in a lot quicker and a lot easier for those. So just one thing to keep in mind, I think, is important, because although the technology is picking up very quickly, what I have no idea what this means, but you know, in your context, but what would it mean to kind of go, you know what, we're just going to grow, you know, one strawberry location, as I think what was just mentioned before, you know, they punch the ground at a certain spacing to allow for the spacing to happen, to give the robotic arms to come in and do it. The next level above that would be, what would it mean to not grow as many strawberries per plant, to space them out a little bit more? So that will reduce yield, but if you've also reduced labor costs, et cetera, does that increase profitability? You know, there's those questions to look at. So yes, the answer is, if you can change things in the environment to make operation or automation come in easier, almost like a factory setting, then that brings in the robotics a lot quicker.
Okay, yeah, that makes sense. Do we have any other questions? Angela, have you spotted any that I've missed?
No, we don't have any in the chat.
Okay. Sala, I do know that you had to run off because you've got another meeting to attend. Did you?
No, thank you. Yes.
Yeah, I was just going to say, did you want to pop your website or your contact details back up on the screen again in case anyone missed it, or are you happy to just scoot off and people can Google if they're fascinated?
No, I'll put the website out there, and if anybody wants to contact me,
beautiful.
I think it's yep. Cool.
Thank you so much, Sala. That has been fabulous. Thank you again for joining us, and good luck, especially in Sydney.
Thank you.
All right. Thanks so much, Sala. So what we might now do is just quickly take a 2-minute break so that you can perhaps scoot off and grab yourself another cup of tea or coffee, literally just 2 minutes, and we'll come back. And up next, we've got Liam from Ultratech joining us. So I'll just put 2 minutes on my clock. If you need to take a pit stop or go and grab a cup of tea, please do so now. You don't need to touch your screen or anything. It'll all stay here. All right, that's my 2-minute alarm going off. Liam, if you wanted to unmute yourself and turn your camera on, that would be amazing. Just check we can hear you okay.
Yep.
Okay, beautiful. If you can hit your share screen button, Liam, then we'll be able to see your presentation. That's brilliant. We can see that, Liam.
Just trying to go full screen.
Yep, no problem. And I'll just remind everyone, if you've got questions, pop them into the chat box. You can type as Liam's talking and we'll just answer the questions at the end of his presentation. Take it away, Liam.
Yeah, no problems. I'll keep this one short and sweet, just so we may be able to squeeze in more question time. So,
Sure.
hi there, guys. My name's Liam from Alteratech. So we're an outfit that was started out in 2019. We were trying to solve a real big question, which is around computer vision in agriculture and accelerating robotics in agriculture as well. So we originally started off basically playing around in both horticulture and broadacre. My background is in climatology and economics, and I've done a lot of study in China, the United States, and the United Kingdom. Most of that being in the US, in like the Salinas Valley and Ventura County, out in California with berries, so Driscoll berries, and a bunch of growers doing lettuce out in the Salinas Valley. Came back to Australia and really started digging into this problem in 2019. And so what we're building is essentially right now we're in the broadacre industry, and you're probably going, okay, what's all this about? So we deal with this stuff right now. It's these big like 48 meter, 36 meter self-propelled sprayers. But we're specifically focusing on weeding and fertilizer application in a precision element. For those in the industry that might have heard about green on green or green on brown spot spraying, where herbicides are applied in a particular place at a particular time as the machine passes over the field. And you can see in the numbers of some of the other companies that are starting to spring up in this space, and some of the research that came out of Blue River, which was acquired by John Deere back in 2017, farmers were starting to see like 80% cost savings in their herbicides alone in the case of broadacre. We're looking to venture back into horticulture. And so the conversation we're looking to have today with farmers is really like, what are the key problems of weeds and fertilizer applications? But I'll go into what we've basically built for the time being, and then we can go from there in terms of the conversation. So yeah, we work in broadacre, and we've built basically solving the problem of going from broadcast spraying to this green on green spot spray solution. We see the weed, we see the disease or pest, and we apply, or in this case, fertilizer as well. We can do variable rate fertilizer and herbicide applications on that crop at that period of time. So we've got a piece of technology that's called YAS. It is a retrofit system. It mounts to a farmer's existing machine. So if you can see those circles on the screen, we basically mount them every 2 meters along a farmer's existing machine. It's a retrofit, so we're not like taking control of the farmer's existing systems or anything like that. It simply sits between the valves that exist on their machine. And so whatever chemistry they're putting down in that field on those particular crops, so if it's anything between glyphosate or a selective atrazine, whatever you call it, it'll put it down in the right place at the right time at up to 30 kilometers an hour. So some of the efficacy of our trials that we're running at the moment, we're seeing a 68% herbicide reduction, and that's including in-crop spraying at the same time. Some projections have already seen a 22% margin improvement. And for one farmer operating out in Kerrang, here in Victoria, they're seeing upwards of a 20% yield improvement, simply because they don't have that crop competition. Their crops aren't competing with those weeds anymore, and they're better able to apply that fertilizer. We don't have a complete fertilizer test at the moment. We've only been focusing on herbicides at the moment, but the data that we're using right now suggests that there can be some really great applications for variable rate fertilizers. Put the right stuff in the right place at the right time, essentially. So the capabilities of this system, it is a retrofit, as I mentioned before, but it's also multispectral. For those that are familiar with like multispectral drones flying over crops or satellite imagery, observing like crop canopies and that high resolution stuff, our cameras can see at a per pixel level, which is basically 1 millimeter, we can see crop health. So we can see red, green, blue, so we can see coloration of fruits and berries. In that regard, but also we can see if a particular crop is suffering from a disease. We can, in the very early stages, with some research that we're working on at the moment, we can start seeing water stress, as well as nitrogen stress problems as well. So as this machine goes over the field, it collects all that data, stores it locally, and it'll process that into a file. And that can be used later for your own reporting, or you can use that for variable rate fertilization as well. It's a fleet learning system. So if you've got, we intend for these to be mounted to autonomous machines. So it's effectively a field scout. It operates day and night, as long as you've got the cameras on and it's got appropriate lighting, which we supply. But it will gather data, it doesn't matter where it is, and it will all collate to a central place and allows us to go global. It doesn't care about what crop it's using. So we've got a bunch of algorithms that we've put in, which is crop agnostic. Originally designed for broadacre, as I mentioned, but it'll work in anything that grows in a row, essentially. This is kind of an example of a smaller version that we whipped up. It's obviously got the cameras removed, but this is a smaller version that can mount to essentially an ATV, or in this case a ute. It mounts to the back with like a 40 or 50 millimeter hitch. You can basically plug it straight into the 12-volt socket in the car, and it will just boot up, and you can run it off an iPad. It's completely wirelessly controlled, and it was the whole design is that you could order this online. It's in a box, you plug it in, and it's good to go. If anything goes wrong, you can pop a couple of the few of the screws off, get a replacement unit, and you're good to go in about 5 minutes. So the whole thing is completely modular. As I said, I was going to keep this relatively short and leave it really much open to questions because we're translating ourselves from broadacre to horticulture. And so I'll leave the email up there on screen, and yeah, I'll open it up to the questions.
Thanks, Liam. That was incredibly fascinating. I haven't spotted a question pop up yet, but I had my own question.
Yes.
You mentioned it could detect disease.
Yes.
How about really, really small pests like mites?
The camera's pixel resolution is 1 millimeter. So if you do push that camera closer to the crop, you might be able to see that. We have, a few people in this space have asked us, can you kick up the resolution? And we are considering, building a system to actually do that, which is custom built for horticulture. Adding those cameras into broadacre is not in a cost-effective manner for that system, but we are considering, maybe tripling the camera resolution for the applications of horticulture for a couple of reasons. Our test farms are combined are about 15,000 hectares.
Mm-hmm.
Some of the lettuce growers and berry growers and fruit growers that we were dealing with out in Bacchus Marsh, I think their combined area was like a few hundred acres, and so the scale differences really allow us to lean into that. I must note that Altera was originally built as a company to solve for the computer vision, and in the long run, we'll be developing into a automation company. So we start off with the computer vision, build up a stable company, and then we'll be moving on to robotics. The idea is that a stable company will keep going, it can keep progressing, and we can keep experimenting. And then we can move into multiple parts of the globe, collect data from multiple farmers, see what we can learn. There's insights that I've gained and weaned from the United States, and there's insights also from Australia. We just simply do things differently here. There's no global totality of doing things. There's a lot of information to be shared. But when it comes to your question, we'll be upgrading the cameras in the not too distant future, specifically for horticulture. And that's kind of why we want to have these discussions as well. Yeah,
for sure. Actually, that leads on to someone else's question here where they've talked about can the cameras be taught to differentiate between pests and beneficials, particularly in IPM situations, I presume.
Yes. That's an area that we worked with out near Kerrang, a place called Normanville. We worked with Melbourne University as well, mostly just asking a bunch of questions about, how can we assist with your integrated pest management stuff? And it was specifically with aphids and ladybugs. Could we detect that? So we basically bought a drone, flew it around and see what we can do with like low canopy flyovers. Drones obviously have the problems they blow the canopy around a lot, and that can make seeing certain things very difficult. But when things are kind of not moving, when you've got an on-wheel tracked machine driving around, that changes up how the game is played. We'd love to be able to do that. That it gets really difficult because these things are so damn small, and you really have to upgrade the cameras in that regard. And so we want to start from kind of we would love to get into that area, and we'll probably start with a big thing first, like helping farmers shift to mechanical tilling, where they can actually use our system to mechanically till weeds, or switch over to something like, I'm trying to remember the name of the chemical. I know it's compound. It's like nonanoic acid, which is an organic herbicide. And so helping farmers switch over to that standard, then we can start garnering all the data, then help with fertilizer and then IPM, et cetera, et cetera. So those real pain in the butt situations are actually the most difficult at times. It's the stuff like herbicides that we can do relatively easy these days. It's just a matter of mechanically getting everything right. So it's within like 95% accuracy or 99% accuracy every time you do it.
Yep. And again, that probably leads on to the next question where someone's asked, can it be altered to the farmer's needs? So in other words, could you, get the machine to do mechanical weeding, picking, any other novel repetitive tasks?
Our job was to act as kind of like we solve, think about it this way. It's just like when you buy like a Toyota pickup truck, wrong country. Like a lot of the parts aren't made by Toyota, right? They're made by all these different people. So we want to solve the most critical thing, which is see the thing.
Yep.
Right. It's like, think of the construction of a cruise missile. Like there's this explosive part, there's this rocket part, and there's this little computer with a camera at the front with a little transceiver and all that jazz. We're kind of building that little transceiver part, and we intend to work with other people that will solve the mechanical tilling or the nozzle thing. So we've actually, that little sprayer, we've actually built this ourselves. It's essentially just aluminium extrusion and pop rivets. And we've built our own solenoid valves to go on it as well as a demonstrator. Some people actually want to buy this thing. So that's a good starting point. And that was specifically for roadside spraying on for our broadacre farmers that we're working with. But we saw that there's this interesting application with vineyards, and a lot of vineyards and fruit growers want to spray under the canopies, just knock out that area under the canopy there, knock out those weeds so they're not really eating into those into their drip lines. And so if farmers want to be able to build a system, we will supply all the correct wiring. Mechanical tillers that kind of pick or spin are actually very simple instruments. And so the engineering around the control systems around that's the most critical factor. So if someone else builds the machine, we'll build the interface for that essentially. So anyone can pick and place these machines. Kind of, if you said, what's the second logo of this company? It is a retrofit. That is our entire idea, is to retrofit to anything out there.
Okay, very clever. Any further questions that people wanted to pop in? Let me just check the Q&A box as well. No, I think I'm good. Angela, you haven't spotted something that I haven't?
No, I think you've got them.
I've had a few messages come through that this is all extremely fascinating and people are really enjoying it. So thank you, Liam, and to our other presenters if you're still there as well.
Yeah, just to give people an idea as well, is like, if you want to reach out, we're happy to have a chat. Obviously, we're based out in Broadacre right now, but we're starting to move into horticulture thanks to our entrance into wineries, table grapes, and nut and fruit orchards. And this is obviously an interesting conversation to be having in the case of strawberries. So we're not doing any of the mechanical picking, but we can certainly do applications of fertilizer, pesticides, etc.
Yeah, oh, and I know there's some blueberry growers and raspberry growers on here as well. So
fantastic.
I'm sure they might reach out to you. And Liam, just to let everyone know, you are based in Melbourne or Victoria, yes?
Correct. Yep.
Okay, just with travel restrictions at the moment?
Yeah, not a problem. Yeah, all good.
Yeah. All right. Well, Liam, again, thank you so much for your time. Even as a non-grower myself, I'm learning an awful lot, and this is extremely fascinating. So thank you again. If you want to stay around, Liam, yes, thank you. Just hit the mute button. Our next speaker is Alistair Mclean from Power Plants. Alistair, are you there?
Yeah, can you hear me and see me okay?
Yes, I can hear and see you. Perfect.
Right.
So, Alistair, whereabouts are you coming to us from today?
South Australia at the moment, but our head office is based in Victoria in Hallam.
Okay, no problems. Well, if you want to hit share your screen.
Yeah, I sure will.
And just while that loads, I'll just encourage everyone, if you've got questions, feel free to pop it into the chat box or the Q&A box as Alistair talks, and he can answer them at the end. So over to you.
First slide, okay?
Yes, I can see that. That's perfect. Thank you.
Okay, so just a little bit of an introduction to the company. I'll be talking about a couple of different technologies from various suppliers that we're the dealer for. That's Priva, Cravo, and IDM in this case. So Power Plants, our goal as a company and what we do is to support growers with technology and services to improve the sustainable productivity of their farms and businesses. Our head office is based in Hallam, Victoria, and we have technicians and a sales team distributed across Australia. we're a full service provider, and I'll get onto that a little bit later. And we've been operating for 27 years. I myself grew up in New Zealand and was always interested in technology around plants and the integration, and started building small automated greenhouses when I was 17. I didn't know what I had to do to get into the industry and pursue that passion. So I studied engineering and started working in greenhouses. And then I moved to Australia and have been working for power plants for 10 years now. And these days I manage the control and water systems division at power plants. So this is our team at our factory in Hallam, and there we have a lot of equipment that we import from overseas, but also manufacture a lot of equipment. We supply not only the berry industry, but also the fruit and vegetable industry, anything with protected cropping. And we also supply a lot of nurseries with potting machines and seeding lines, and that's the other side of the business. And these are our locations around Australia, so you can see we're fairly well spread, where technicians and salespeople are located. So what we're known for really at this stage in the berry industry is providing automatic fertigation systems. And we've got systems that are applicable to in-ground growers, such as the neutral one on the very left-hand side, all the way through to growers that are growing in substrate in berries, and then also in vine crops and substrate also. Preva, the company that we represent, actually have a venture in robotics, but this is based around the vine crop industry. And I just wanted to play this short video just to give you an idea of the actual robots that they've been developing for that industry. And at this stage, they're focusing on tasks within greenhouses, such as deleafing, which is what you can see the robot doing here. And these robots are being used by commercial growers in Holland. And there's, of course, a future plan to roll that out across the rest of the world. We see Australia as a high wage country. So all the growers in Australia that are growing greenhouses that grow vine crops are hoping that these robots are on Preva's bucket list for delivery to Australia. So that gives you an idea of what Preva do. It's not just fertigation systems, but also have a venture into robotics. What I want to talk to you about today is the low-hanging fruit of automation, which is already available now and being widely used in the Australian berry industry by a number of growers. And that is automatic weight-based irrigation. So when we're talking about robotics, we're talking about automation. How can we improve, reduce labour, reduce mistakes, and improve yield while reducing input costs? And automatic weighing of the crops and irrigation based on that weight measurement is something that I'm going to focus on in this discussion. So typically growers growing berries, with time-based systems using fixed start strategy times, each day, fixed irrigation intervals, a fixed stop time each day, and it doesn't really take into account our constantly changing climate and weather. So definitely this approach will allow you to grow a crop, but lots of manual changes need to be made on a constant basis if you want to get a better result. And the grower has to sort of in some way predict what's going on with the weather in order to make those manual changes. And then there's lots of checking that needs to be done manually, drip and drain measurements. And in this case, I'm talking about when it comes to the grow scales, I'm talking about substrate-based berry growing. But I've also got some information about growing in ground as well. So what's the next step that we take? The next step is that we use a solar sensor to measure the radiation, and we take that into account so we can irrigate more regularly automatically when it's sunny versus when it's cloudy. And that's a great step in the right direction. But really, at the end of the day, we're only taking into account one of the 4 drivers of transpiration. So what do I mean by that? Well, solar radiation is definitely a big factor, but also there's temperature. What happens when it's a cloudy day, but it's hot? What are our plants doing then? What happens when the wind picks up, and how does that affect our transpiration if we're only using solar radiation to trigger our irrigation? And even humidity, especially in different seasons. So how can we calculate, is there some perfect formula where we can take, temperature sensors and wind speed sensors and try and calculate the transpiration rate of the crop? Well, a very simple way of doing this is to weigh the crop. And by that, I mean weigh a portion of the crop that's a representative sample. And the beautiful thing about that is that 1 mil by definition is 1 gram. So it doesn't really matter if we see water being absorbed, we see, you know, the grams being reduced on a scale system. We know the plants are absorbing water. It doesn't really matter to us whether it's because of any of the 4 drivers, because they're all playing their part, and that's why the plant's drinking water. So what do growth scales look like? So here's a few different examples. On the left, you see it in a strawberry setup with a couple of bags on a scale system, a load cell at either end. And then you can also see a setup on the right-hand side with blackberries and with larger pots with a larger scale. And the first sort of question is, okay, well, do I have to run cables out into my field? And the answer is no. So these wireless scales are all, they're all wireless. So you can send from these scales both the weight measurement, which is the average of both the load cells, but also the drain measurement. So there's a drain sensor that records the amount of runoff off the scale system and can tell you when you first have drain during the day. And the climate computer can also, based on that information, calculate what your percentage drain is for each irrigation, and also your 24-hour drain for the day. So this information, both the weight measurement and the wireless drain measurement, are sent back wirelessly to a receiver. Ranges around sort of 300 meters, but you can put extra repeaters in if your bags are, or where you want to sample is further away, and that will give you another 300 meters range. So they can be extended across the farm if you have a large farm. So how are we going to take the weight measurement and then figure out the best way to automatically irrigate? Well, the first thing the system will do is it will look at the drop in weight in the morning, and that gives us an indication of when the plants are starting to drink. Just like us, you know, if the plants haven't woken up yet and we try and feed them, if someone, you know, ripped your duvet off and tried to give you breakfast at 3 a.m, you might not be too happy. The plants don't react too well to that either. So, you know, a lot of people have a fixed irrigation time every day, and a lot of people probably don't change it. Whereas with the growth scale, what it will do is it will automatically determine when the plants are drinking, and it will irrigate at that time. And so that's a setting that you can put into the system. So obviously on a sunny, you know, windy or dry day, that irrigation time is going to be earlier in the day. And then on a cloudy or foggy day, of course, that will automatically be later in the day. So once we've had our first irrigation of the day, the next thing that the system will do is it will allow you to put a setting in for how quickly you want to wet up your bags or slab to the drain point. So that steepness of that ramping can be adjusted depending on whether you want to get drain after a couple of hours or maybe even only after 1 hour. And the system will automatically follow whatever that setting is and wet up from there. So then we get to the period where the plant has first had some drain come out. So, so basically when we first get drain, the scale will automatically recalibrate what it calls the saturated weight so that it can then in the afternoon dry back, and there's a setting for that. So during the drain period of the day when we first get the drain, in the system we can program the amount of drain that we would like to receive before we then start to dry back. So that will achieve 2 objectives. One objective is that it will allow all the plants in that area to be even. And what I mean by that is that if we give continuous irrigation and achieve drain, maybe where the growth scale is placed is the average of the crop, but you might have some bags on the leg rows where you're getting more drying out, and maybe those ones haven't got to drain yet. So we're going to give extra irrigation until those ones are saturated. And vice versa, you might have some in the very middle of the tunnels where humidity level is higher, and therefore they might have got drained before we even saw drain on the scale. But by giving a couple of extra irrigations and achieving drain, we're able to make every single bag in that whole area even, because it can't be any more even than when all the bags are saturated. So once we know all the bags are saturated by giving an extra amount of drain, the other thing that a lot of growers like to do is, of course, flush the salts from their bags, so we can have a programmed extra amount of irrigation, so that the growers are comfortable that their system has flushed, the salts out, and then from that point we can start drying back. So when we dry back, what we're looking at is that calibrated saturated weight. And then we're saying, well, we want to, in the afternoon, we don't want to still be saturated. We want to maintain a good oxygen to water ratio. We still want some good amount of water in there, but every irrigation doesn't need to lead to drain. So that's where we have our afternoon dryback setting based on a weight, and that will allow us to dry back to that point automatically. So you can see that the system is only going to irrigate when it hits the green line. So as it's drying back, only when it gets to that point will it give another irrigation. And then the last part the system does, and I think this is one of the more incredible things, is that you'll also have a nighttime dryback target, again to maintain the perfect oxygen to moisture ratio. So in the nighttime you can set a target. And what the system will do is, if it needs to, let's say, achieve a further amount of dry out by 5 or 6 p.m. whenever your sun goes down, then it will be looking at that afternoon dryback and it will be irrigating when it hits that line. But it will also be looking at the evening or nighttime dryback that you've programmed, and it will automatically stop the irrigation based on the transpiration rate, so that it can dry out and hit that, that evening or nighttime dryback target. Another thing that the system can do is, if there's certain days or times when you want to flush some extra salts, is in that drain period that's in the middle of the day, there's an optional setting that you can actually set it to flush. And what that will do is, rather than achieving your normal amount of drain in that drain period, it will instead achieve a high amount of drain that you set, and then the next day it will automatically go back to the normal amount of drain. So that's a nice option, and something that a lot of growers utilize. So this is a screenshot of a grower's system that's working automatically. And what that shows you, the blue line, that's the calculated weight. And then the red line, that's the measured weight that the system is wirelessly sending back to the climate and irrigation computer. So as you can see, in the morning, when we get past a certain time, it's then starting to look at whether the plants are drinking or not. So you can see that red line just dipped, enough below that blue line that it triggers the first irrigation of the day. Then you can see that it only irrigates based on that ramping, the steepness of how quickly we want to wet up. And the red line, again, as soon as it drops below the blue line, it then irrigates. Then you can see it goes into the drain period. Down the bottom, you can see that the blue line is the dark blue line is creeping up. That's the measured drain. So we can see when we get our first drain, it then gives some quite regular irrigations. And that's achieving a set amount of drain that the grower has asked for. And then once we get to the, in his case, it was just after 11:30, he wanted to start drying back. So that's the afternoon dryback. You can see the blue line, light blue line is decreasing. And then again, it's drying out to, and only irrigating when it drops below that blue line. And then in the evening, you can see that it's around the sort of 4:30 mark. That blue line drops down again. That's the evening or nighttime dryback target. And you can see in the afternoon, even though it drops below that blue line, what it's doing is it's realized that in the evening we want to dry back, further than that. And if I don't stop irrigating at some point, I'm still going to be too wet. So it automatically knows when it needs to do that. So one of the things that is already quite widely used in the berry industry is moisture sensors. And one of the questions is, well, why don't we just use moisture sensors for these sorts of applications? And moisture sensors are a great tool. They do make sense to people. It's just 0 to 100% moisture, right? The readings can change depending on where you put it. So that's a downside. If you pull a moisture sensor out and you put it back in, often you'll get a different reading. If you compare that to something like a grow scale that's measuring weight, 1 gram is 1 mil, so there's no hiding, there's no trend that we have to look at to establish what it really is. At the end of the day, it's an absolute measurement. And also with moisture sensors, there's no drain measurement, and having the drain runoff, percentage and measurement is a really nice tool to also tell us when the bag is saturated. So in summary, it's a great tool with moisture sensors, but not 100% reliable in substrate. However, when it comes to in-ground growing, and I'm sure a number of people are growing in the ground, moisture sensors can be a great tool to wirelessly transmit information back to a computer and automate the irrigation based on that. So we've provided a number of systems around the country with in-ground growers that are having good success. We provide a 15 centimetre long probe, which gives you good cross-section and contact with the soil. And often we have multiple probes connected to one transmitter so that they can take an average. And then that can be wirelessly transmitted back to the computer, where for each period of the day, we can set different moisture targets, and the irrigation can accordingly give smaller shots than probably a lot of in-ground growers would give, but just sort of gently build up the moisture in the morning, and in the evening, or afternoon, start to look at drying back a little bit. And just having that control definitely has, for a number of customers, lead to a much better utilization of their input costs, water, obviously, fertilizer, and of course, the better, yield and quality from more correctly irrigating based on what the plant demand is. So back to grow scales. So this is a side-by-side comparison of a customer that was using light and time to irrigate with an irrigator that was keeping his eye on the ball. That's the pot on the left-hand side. And then the automatic grow scale on the right, where the plant was just left to do its own thing based on the initial settings that were put in by the customer. And as you can see, when you can control and measure in such a precise manner exactly what's going on at all times, you can really walk a much finer line and really just irrigate based on plant demand. When you irrigate on light and time, most growers will give extra irrigation because they can't really figure out 100%, what the wind is going to do, what the temperature is going to do, what the humidity is going to do. So most people will give extra irrigation or a little bit of a longer shot to take into account, hey, look, it might dry out a little bit more than I think, and the last thing I want is the plants to wilt. But the result of that extra irrigation is always that the plants, the roots are going to be effectively more lazily. They become a bit like spoiled children. And compared to the right-hand image where the plants, the roots are only getting just the water that they need at the times that they need them, they of course go in search of that water. So you can see on the right-hand side, we have much more prolific root growth. And when we've got bigger roots, we have a number of benefits, such as allowing the plants to transpire more, leading to greater nutrient uptake and more growth and more production. Of course, when conditions are stressful, like in summer, the plants can cool themselves better on a hot day, but because they have more roots, they can absorb more water and transpire more, leading to lower stress levels. Fruit quality is improved. Problems of soft fruit are reduced, especially by irrigating at the right times, and especially in the morning when, if we don't irrigate at the right times, if we irrigate too early, then we can lead to guttation and other issues. And then the plant health is improved because stress levels are decreased, along with diseased and other things like that can affect roots when they become unhealthy, if they're waterlogged at night because they haven't dried back properly, because we haven't stopped irrigating at the right time in the afternoon based on the conditions. And then of course inputs are better utilized as plants are being irrigated with the exact amount of water. We're not giving extra water, there's not heaps of drain running off everywhere. We're just giving them what they need. Of course we do need some drain, but we're calculating and predicting how much we need. And every time we irrigate, of course, we're using fertilizer. So if we can reduce our fertilizer need, then that's a benefit as well. So that's a bit about the sort of the yield and the quality, but what do customers tell you about the system? What do they tell us? One of the things is that, you know, in substrate, a lot of people have manual drain stations, and a lot of people will run around the whole day doing their trip and drain and constantly monitoring, and that takes a lot of labor. So not having to, you know, constantly check that drip and drain because the scale is giving them the information that they need is a great benefit. Grow scales pick up on rapidly changing water requirements with crop when it fruits. So we had a grower in Coffs Harbour who went from using 8 litres a pot per day to 13 litres of water per pot per day, automatically on the scale within a couple of days. And that was when, of course, the fruit was coming on. And in the past, he was, you know, giving that increase, but he was spreading it across sort of 2 to 3 weeks, just gradually increasing it every day. But when he installed the scale system, you know, the scale was doing what the plants wanted. The plants were determining the irrigation that they needed, and they wanted that over a couple of days. And the result was, in the past, he was never able to get all of the fruit off. You know, there was always some sort of failings in that. And you know, when he put the grow scale in, that was the first year that he got everything off, and he was super chuffed. Of course, reduction of disease is really important, you know, due to not being able to irrigate correctly because of not having the right information coming back. So if the irrigation is mismanaged and we do have really wet roots overnight, for example, then of course that's going to lead to disease. Short irrigations at night, which was really interesting, on warm nights, especially in regions that are warm like Coffs Harbour. When the wind's howling at nighttime, you would be amazed about how much transpiration actually occurs. And so growers are using the grow scale system to automatically give very short irrigations at nighttime, so that the substrate doesn't dry out. And so they're starting at the right point in the morning before they give their first larger irrigations of the day. The last bit of feedback is the grow scales always keeping them ahead of the curve. So they're getting information really before it happens. When you do your drip and drains, you're always looking at what just happened from our previous irrigation and trying to work out what we need to do next. Whereas the grow scale is the opposite. It's presenting you with the information of what's happening right now, so you then can make the best irrigation decision at that time. And due to these benefits, power plants have installed over 80 grow scale systems for berry growers across Australia. So it is a technology that's been widely used by growers and to great benefit. So all of this technology and all of these settings, this must look pretty complicated, right? And as you can see, there are a number of settings that have to be entered. And as a provider of this technology, power plants consult with customers over several weeks when they purchase a system like this, and log in every day so we can see what the scales are doing and advise how the settings can be set accordingly based on our experience. However, what we do is we have made pages like the one that you can see here that have all the settings on them and have pictorial or animated overviews that allow you to understand what setting you're putting in and what that affects in terms of you know, the wetting up or drying back of the system. So that's what I had on grow scales. I just wanted to mention a couple of other technologies, you know, that are automating the way that we're approaching growing strawberries in Australia. So one of those is actually in Victoria at ASD. They have a retractable Cravo house, and power plants are a partner with Cravo. And some of the reasons, you know, you're comparing to a tunnel, of course, a retractable roof structure where the roof automatically opens and closes based on the weather conditions. Of course, that's going to cost more than your basic sort of tunnels. However, when you look at the ROI of something like that, it's not just about, you know, do you improve your yield and does that pay the whole structure off? Where this has been of benefit has been by allowing you to hit the window, you know, being able to get into the market earlier and stay in the market until later. You're not competing with all of the other regions around Australia. You're picking your slot, and obviously when prices are highest, if you're able to lift the quality of your crop and especially lift the A grade pack out yield, then that's been of significant benefit to customers that have invested in this sort of technology, where the roof automatically opens and closes to allow the full amount of light in when the conditions are perfect. Obviously, in a tunnel, you've always got that permanent covering there. So what happens with that is, of course, we're always going to lose light. And by allowing all the light in when the conditions are right, that's what's also led to, improvements in yield. Also improvements in shelf life when the fruit is not in a really humid environment, which it can be in the middle of a tunnel, less soft fruit, and improved bricks levels as well. Some side benefits to this, of course, is with greater airflow, which you definitely get in a structure where the entire roof retracts in sections, then you get less disease and you have to spray a lot less. This is sort of the next step. It's not saying let's grow strawberries in a glass house, with a heating system and spending, countless thousands or most likely millions of dollars. Instead, it's saying, let's take that next step. Let's take an appropriate technology that allows us to grow in a more automated way and have the benefits of better quality and better A-grade pack out in the window that we want to operate in. Here's a couple of photos from these sorts of projects. And on the left-hand side, you can see a picture which is comparing the tunnels, which is the bags on the left-hand side. That's where those strawberries were grown, and the Cravo house, that's the bag on the right. And you can see, of course, on the bag on the left looks very impressive because the plants spend a lot of time growing a lot of leaf. But what do we get paid on? We obviously get paid on the amount of fruit that we produce. And you can see that the plants on the right-hand side are more generative in terms of they're producing more strawberries. The plant on the left is a very vegetative plant. And so you can already see that the plant on the right-hand side is at an earlier stage. And these plants were put in, one in the Cravo house, one in the tunnels, planted at the same time. That I wanted to share with you was the use of smart spraying systems, where the actual spray, the liquid contents in the machine that is driving, and it allows you to, you'll see as we go further through the video, the actual spray broom is completely retractable and adjustable. So you can see now it's spraying with a shorter row or 2 rows on the left and then 3 rows on the right. And also with booms that or spray nozzles that go down in between and then spray upwards. And these self-contained units are quite nice for driving around the farm. Especially you can see the planting densities that are able to be achieved, given that it's a very narrow spacing in rows, because you've got to leave a larger row because of your tractor. Then putting an extra row might give you a lot of extra yield over over a hectare, for example. So we can see that the system is adjustable in height, and also the booms are retractable and adjustable when spraying in the tunnels. So these spraying solutions, they provide a totally homogeneous treatment. They're extremely maneuverable, these sorts of spray trolleys. They're very narrow, 75 centimeters with a wheelbase of 85 centimeters. But of course you can see those wheels don't come up very high. Booms are available in 6 meters to 9.2 wide. And then horizontal and vertical booms are available on the same machine, and the spray machine can hold 400 liters of liquid. One of the questions is, it'd be really nice if a unit like this had a cab on it, and I understand that a lot of growers in Australia would like that. But unfortunately, as soon as you start adding cabs and air conditioning and these sorts of things to a unit like this, that's when you really end up back to a tractor in terms of the size of such a machine. So that's another, I suppose, automatic or slightly robotic way of approaching spraying. So I'll hand it over to some questions, but yeah, I'm Alistair, based in South Australia. I look after the Control and Water Systems division at power plants, but we also have an account manager, of course, in Victoria. His name is Rocky, pictured on the right, and he's already speaking with a lot of customers in the strawberry industry.
Fantastic. Thanks, Alistair. Angela, I can see a few questions there in the chat box. Do you want to run through them?
Oh, sure, I can do that. Okay, so Sam's asking, can the scales be used with other computer systems, or do they have to be linked with the Preva run equipment?
Sure. I mean, of course, it might be interesting to put some manual scales out in the crop and just see how things change over time. But really, the scale system is one part of the solution, but it's really the technology and automation that the Preva controller provides that allows the benefits of being able to automatically schedule the irrigation. And that's in the brain of the Preva computer or control system. So really they need to be together to get these sorts of results. However, one thing I would say is if someone already had a irrigation system from another provider, it is possible to retrofit Preva sensors onto that irrigation system, and then the Preva controller can control that irrigation system. So that could be a way that someone can start using scales. Yes, they have to replace their control system. However, they don't have to replace their whole, fertigation or irrigation system.
Okay, thanks for that. Also, do the drain stations have EC and pH sensors on them to determine what's coming out? Or I've missed one.
Sure, that's a really good question. It is possible to do that with a wired system. However, when we're talking about wireless, the wireless scales and drain sensor systems, one of the factors there is we don't have a huge amount of available power. They are run off batteries. So an EC sensor and a pH sensor unfortunately use quite a lot of power to continuously measure those measurements. And because of that, it's not something that we can do with wireless at this stage. However, if you're prepared to run some cable out, then we can definitely have EC and pH measurements as part of that. One other thing to mention though would be there are wireless moisture sensors that also measure EC and slab temperature that can be integrated with the system so that you could get at least your EC measurements in the slab as well.
Okay. And does the scale, does it detect plant weight? So the weight of the plant fluctuates during harvest?
Yeah, exactly. So that's a really good question. And usually the first one you get, hey, look, it's great to weigh all this stuff, but how do you know it's the water that you're weighing? And the answer to that is every day when we irrigate, we get to the point where we get drain. And when we get drain, the total weight of the slab plus the water that's in it, plus the crop that's on top of it, it can't be any heavier than that. And so then all of the, every time that the system gets drained, it recalibrates its saturated weight. And then all of the settings for dryback, for example, are subtracted from that saturated weight. So as you can imagine, let's say as the plants grow, every day that saturated weight might be a little bit heavier. But because we're taking that saturated weight and then deducting effectively the amount of mils or grams or kilos for our dryback in the afternoon and the evening, we're recalibrating it after every irrigation that leads to drain, and therefore we're able to basically get an accurate deduction of weight for our dryback that will only be related to the moisture, or the water, or the amount of mils or transpiration that the plant is transpiring.
Okay, thanks, Alistair. And with the little sprayer, are there any designs that spray from the bottom up in tunnels?
Yeah, so the video that I shared, a little bit hard to see because the resolution wasn't great, but it actually had the spray broom has the spraying nozzles that are from the top spraying out, but it also has little droppers that go down in between the rows and then spray up. So it actually sprays from the bottom and the top.
Great, thanks. Does anyone else have any other questions?
I haven't spotted any others either, Angela. So, Alistair, if you just wanted to stop your screen share, that would be great. So I just wanted to take the chance to quickly thank everybody again for coming along and giving your presentations. Massive thank you to Alistair, that was really fascinating, and Liam, I can see, is also still here, and also to Joe and Sala, who I think might have left. But again, thank you to our incredible presenters today, and thank you to everyone who came along, and I'm sure you learned something and took something away. Even as a non-berry grower or as a non-farmer, I found this extremely fascinating, and I certainly learned a lot. So Alistair, thank you again for your talk. I'm not sure if you're there anymore, Alistair, but thanks again to everyone else. And Angela, thank you for helping me with fielding questions as a panelist as well.
No worries.
All right, well, I suppose we'll all hang up now and disconnect. It seems so odd.
Thanks very much for the opportunity to be a part of it.
No worries, Alistair. Thank you again. And thank you, Liam, too. Thanks everyone for joining. I'm going to turn the webinar off now. Thank you.